So this is the pigeonhole principle. If you have a set of objects and a set of containers, I like to think of the objects as the pigeons and the containers as the pigeonholes. If you have more pigeons than pigeonholes, then some of the pigeons have to share a pigeonhole. Here's some basic examples. If you've got 3 people that are trying to go somewhere and they have to fit into 2 cars, then you know that at least 2 people have to share a car. Now, it could be that there's 3 people in one car and no one in the second car, or you could have 2 people in one car and 1 in the other. There are a lot of possible situations, but you know that one of those cars will have at least 2 people in it. Another example, if you flipped 5 coins, then you know that at least 2 of those coins have to match. In this case, the coins are the pigeons and the outcomes, which are heads or tails, are the 2 pigeonholes. You can't guarantee much. You can't guarantee that there will be 2 heads. You can't guarantee that there will be 2 tails. You can't guarantee that there will be exactly 2. You could have all 5 heads. You could have 3 heads and 2 tails. You could have 4 tails and 1 head. So many possibilities. The only thing that you know for certain is that at least 2 of those coins are going to match. I want to phrase this a slightly different way because I believe if we write our solution this way, it's more useful for other problems. If each coin were different, if each coin had to have a different outcome, well then one coin could be assigned heads and one coin could be assigned tails, but then there's 3 coins left over and we have no outcome for them. So that means that at least 2 coins have to match somehow. I'm going to use that style of proof to solve this problem. If you flip 5 coins, then at least 3 of them have to match. So if only 2 coins are allowed to match at a time, that means that 2 coins could be heads and 2 could be tails, but then there's 1 coin left over where you have no outcome to assign it. So that means that there has to be at least 3 that match. In an entirely different situation, if you have a list of 70 different English words, what is the highest number of words in that list that we can guarantee are going to share a first letter? And this is a bigger, messier problem. You have 70 words, you have 26 letters. These are much bigger numbers. And what's worse is I have to start working up from 2. But it's okay. I can guarantee that at least 2 words will share a first letter. Because if each word has to have a different letter, that uses up 26 of the words. You'd have 1 word that starts with A, 1 that starts with B, 1 with C, 1 with D, 1 with E, and so on and so forth. You use up 26 of those words, but then you've got these 44 leftover words and you have nothing to start them with. So that means that at least 2 of those words have to have the same beginning letter. In fact, you can guarantee that at least 3 words will share a first letter. If only 2 words at a time are allowed to share, you can use up 52 of your words that way, but then there's 18 left over. You think, well, can I guarantee that 4 words will share a first letter? And the answer is no. It is possible, not guaranteed, but possible, that you could have 18 sets of 3 words that share, and then 8 sets of 2 words that share. So for example, if A through R all had 3 words each, and S through Z had 2, well that's 70 words, and none of the letters have a team of 4 words, right? So you can't guarantee 4. Now, it's entirely possible that your list of 70 words all begins with T, so T gets 70 and all the rest of the letters get 0. But that doesn't mean that you get to answer with 70 because you can't guarantee that 70 will share. It's just one remote possibility. The only guarantee is that there will be at least 3 that share at least one of the letters.